the AMATIC 2015 webinar series. My name is John Oakes, and I'm the Professional Development Coordinator for AMATIC. And today's presentation is integrating the mathematical practices in mathematics for elementary teachers courses by Dr. Meg Moss. And this presentation is sponsored by the Teacher Preparation Committee of AMATIC. And AMATIC is the American Mathematical Association of Two-Year Colleges, and our core value is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And for more information, please visit our website at amatic.org. And please note that the views expressed by the presenter are not necessarily the views of AMATIC, and any commercial products mentioned by presenters are not endorsed by AMATIC. And WebAssign is proud to support the AMATIC webinar series. And now we're going to switch to the presenter slides. And before we get on with our presentation today, let me introduce our speakers. So Meg Moss earned her PhD in mathematics teacher education from the University of Tennessee, Knoxville, Master's in Math Education from Appalachian State University, and Bachelor's in Secondary Math Education from the University of North Carolina, Chapel Hill. She taught for 8 years at Treasure Valley Community College and 10 at Mississippi State Community College, and she is currently a faculty member with Western Governors University in exploring how to integrate the mathematical practices into an online environment, and she has taught math for elementary teachers courses for most of her teaching career. Meg lives in the beautiful Blue Ridge Mountains of Asheville, North Carolina, and has 2 wonderful teenage sons. So let's give a round of applause and welcome to Meg Moss, if you haven't already, and now I'm going to turn it over to you.
Hey, John. Thanks for that. Thanks, everybody, for being here. John, can you pull over that poll question about a scale of 1 to 5, first of all? And also the web link to the PowerPoint slide. So if you guys will take a minute and just fill out this poll, and then if you would like to have the PowerPoint slides, some people like to have them on their own computer to run or to refer to later. If you click where it says PowerPoint slides right there, then the Browse To button will open up and you'll be able to go pull those up. You can hardly hear me. All right, thanks for that, Jan. Let me adjust my... Do I need to go higher, lower? Great. Okay. So the poll is open now. Fantastic. You guys let me know. I need to adjust it more. And these are all anonymous results that you have here. All right. So it looks like we have a range, which is always interesting. Again, if you want to pull down the PowerPoint slides, click where it says PowerPoint slides, hit Browse To, and that will take you directly to the file. All right, fantastic. So looks like some of you are right in the middle, and we could do some analysis of that, but we won't. So fantastic. John, if you could pull that poll away and the web link, if everyone's had a chance to grab that PowerPoint if you want it. Thank you. All right. Okay. So the first thing I want to say about this is to be or not to be a Common Core state, right? Because this is in the news, it's in wherever you look, right? And some of you might be in states where you haven't adopted, you're going to adopt, or you did and now you're going back. Okay. So right now, as of last night, there are 43 states that have adopted the Common Core state standards. The states that have not officially adopted them, they have similar practices. Case in point is Texas. Texas has the essential knowledge and skills as their curriculum standards. And these include 7, they call them mathematical process standards, which read a whole lot like the mathematical practices of the Common Core. So it's still the same type of mathematical thinking. And then there are states like my very own state of North Carolina that are saying, okay, yeah, we've implemented the Common Core, but now we want to see, okay, do we really want to do it, right? In the states that are in that space, from the research I've done, the states that are in that space, what they still are looking at something like the mathematical practices. So whether we call it Common Core or whether we call it whatever, it's still a similar concept. So let's move on and talk about these. So the mathematical practices of the Common Core, 2 of the documents that were used to create them were, of course, the top one that I imagine we're familiar with, the good old Principles and Standards for School Mathematics by NCTM, National Council of Teachers of Mathematics. So they had their process standards, right? The problem solving, reasoning approved, communication, connections, representations. Adding it up from the National Research Council had the strands of mathematical proficiency, conceptual understanding, procedural fluency, strategic competence, adaptive reasoning, productive disposition. So these are all very related. They're all, adding it up had a nice visual of like strands of a rope that all of these like intertwine. So none of them are mutually exclusive. But from all of that, they came up with 8 standards for mathematical practices. And this is kind of a nice way to organize them. That's put out by the National Governors Association Center for Best Practices and Council of Chief of State Officers, of kind of grouping these 8 mathematical practices. And so I found this chart useful of grouping 1 and 6 over there on the left into overarching habits of mind. The reasoning and explaining is mathematical practice 2 and 3. Modeling and using tools is 4 and 5. And then seeing, structure, and generalizing is 7 and 8. So we're going to be going into these. I'm going to use this framework, this organizational tool, and we're going to delve more deeply into these. And please, please share your ideas as well. Okay, I'm going to be pulling up a poll regularly so you guys can share your ideas about these practices as they relate to our Math for Elementary Teachers courses. Okay. And then this is really the same chart, but it's it's cuter, and it's more looking at maybe elementary students and what these practices mean more for them. So at the top we have the overarching habits of mind, and you guys have the PowerPoint, so you guys can study this in more detail later. And then along the bottom you've got the reasoning and explanation, in the middle the modeling and using tools, and then the seeing, structure, and generalizing. So you guys have this chart so you can study it more fully. But let's, some of the questions that I've been wondering about and that I'm hoping we can discuss and think about here is, what implications do these mathematical practices have on our Math for Elementary Education courses? So what do you guys think about that? Put in the chat. What do they have to do with our Math for Elementary Ed courses? Why should we care? Really, the question could be asked, what do they have to do with any of the courses we teach? everything is very integrated. And these mathematical practices are really integrated. I really struggle with, okay, do I put this problem under this mathematical practice or under this one? Because they're all so integrated. Exactly. Okay. And then something we're going to be talking about today, and I'm going to ask you guys to share your ideas, is what opportunities can we provide to our students to help our students become mathematically proficient, to use the Common Core language. Is how can we help our students to be this type of mathematical thinker that the mathematical practices call for? That's what we're going to be sharing ideas about today. And then how can this in turn lead to our students creating opportunities to engage in MPs for their future students? Because there's a big phrase that I'm sure we've all heard that says, is that we teach the way that we were taught, right? And if students experience math with lecture and regurgitating information versus mathematical thinking, then it's probably how they're going to teach math. And yeah, you're right, Colleen. Many of us have already been doing this. The NCTM standards. Well, the first iteration came out in 1989, and then the next iteration was in 2000. So it's nothing new. It's been systemized. It's directly been put into curriculum standards. It's what math teachers out there in the K-12 schools, it's what they're expected to incorporate all of these things into their classroom. And it's part of their evaluation now. Exactly. All right. So, I know you guys have lots of great ideas to all these 3 questions. I know they're large questions, but in the interest of time, let's delve more deeply into each of these mathematical practices. Okay. So the first grouping, the overarching habits of mind of a productive mathematical thinker. Okay. Joe, I think that it depends. I think teachers, like Colleen said, haven't we already been doing this? I think teachers that embrace the NCTM standards and adding it up, I think they have no problem with it. I think a lot of teachers are terrified. I spent all last year studying and working with high school teachers to implement the Common Core, and they're terrified of giving up time. That's one of the biggest challenges is I don't have time to do this. I don't have time to spend an all class period working on 1 or 2 concepts. And so that's a huge problem in the schools. It's because they're being judged on that end of course test or whatever your state calls it. And they're not willing to believe. I mean, I can talk to them all day long about research that says, a mile wide and an inch deep doesn't work, right? But they're really scared, really scared. Yeah, nice comment, Brenda. Okay. So overarching habits of mind of a productive mathematical thinker. So we've got the first one, which says make sense of problems and persevere in solving them. And MP6 is called attend to precision. And John, can you pull over that link to the mathematical practices, web links to? So that's the link actually to the mathematical practices of the Common Core. So you guys can probably find that anyway. But if you want to go read the actual phrasing of it, you can go to that link there. John, maybe you could kind of move that down into the corner so people can still have access to it. Thanks. All right, so let's look into this mathematical practice 1. Make sense of problems and persevere in solving them. So my interpretation of what this says, and that's part of it, is, boy, what did they say? They're hard to read, okay? And so I've done a lot of reading, a lot of researching into what other people think they say. And this is what I've come up with. So students look for a place to get started in a problem. They think, they try, they assess, they try again. They connect problems to other problems they have done, and they simplify problems. So, and the last one here is they check their solutions and their strategies. So, what do you guys think? And John, can you pull over the other poll question? Yeah, that one. So, before, and can we kind of move it to the corner so they can still see the slide? And so I'm wondering, in what ways, what are some ways that you and I and all of us can facilitate our students in becoming mathematically proficient as related to this mathematical practice? I have some ideas I'll share with you, but I want to hear your guys' ideas first. Nice ideas. Any others out there? And that students need to struggle. They have a hard time with that, don't they? I call it the Google generation. We're so used to instant answers, right? And to sit there and struggle with a problem is not something they're comfortable with initially. They can get comfortable with it, but it takes time. Yeah, there's non-routine problems, but there's problems that are accessible, right? That they can figure out given the right tools. They totally can. Nice, nice. Yeah, diagrams, pictures, manipulatives, all those things can help make sense of problems. And I think I've already said this, but the mathematical practices are not mutually exclusive. They're all so related. Okay. Thanks, guys, for sharing. John, if you can move that out of the way, and we can probably go ahead and move the web links too out of the way as well. Thanks. Okay. So, yeah, I agree with everything you guys said. The big thing here is, which is related to what you guys said, is that we have to help students make sense of the mathematics, not memorize the procedures. And so often, I think especially with these math for elementary ed people, they say, just tell me how to do it. Let me memorize that. Okay, I have to memorize these steps. And I say, no, you don't. You have to make sense of it, not memorization. So you have to really help students see that, yes, I can make sense of this. I don't have to memorize it. I think we have to work on encouraging positive beliefs and attitudes about math and themselves as math learners. They say they hate math. I'm not good at math. All those phrases we hear from our students so often. We have to stop that. I don't allow my students to say I hate math. I don't allow my students to say I'm not good at math. I say, yeah, you are good at math. Everyone can do math. And we have to help them believe that. That's huge with these students, as you guys well know. They're terrified of it. And I think when I first read this mathematical practice, the one thing that popped out at me was, this is a lot of the POYA's 4 steps of problem solving, right? Understand the problem, figure out what you're going to do it, and then look back and make sure your answer makes sense. So I think really helping our students to work through those steps, really think about it, be intentional about it, can be a way to help them have some strategies to get there. I like this problem is related to the mathematical practice one because somewhere I read something about it's like thinking outside of the box, right? Students have to be able to think outside the box. I love this problem. Without lifting your pencil, go through all 9 dots, but you can only draw 4 lines. I'm not going to show you guys the solution. I'm going to let y'all play around with that one. Okay. Play around with that one. But that's one that, okay, you could usually give up or you could think outside the box. That's your hint to that one. And draw those. And Julie, yeah, I love POYAs too. Something I've done with students a lot is ask them to think of a problem they've solved, not a math problem, but a real life problem. And what steps did they take to solve that? Almost always they can come up with basically 4 steps of problem solving. So math is a problem-solving journey. I like that phrase. Okay, so mathematical practice 6 is titled Attend to Precision. And it basically says, and again you can read the full text, mathematically proficient students communicate their mathematical thinking. They articulate clear definitions and meanings of symbols, and they use correct units of measure, and they calculate accurately and efficiently. So in my mind, sometimes this one, we've all heard of, they have to know how to do it pencil and paper. And yeah, they have to be able to calculate accurately and efficiently. All right, so that's included in here. So John, can we bring back over that poll question, and so people can add to the ideas of maybe move it down a little bit. Move it. No, I can't move it. Move it down so people can still see the text. And let's just add to this. So what are some ways to help our students get to this, to become this type of student? Because most of them come to us not able to do this. So type our thoughts about that in the poll. Writing in mathematics is important. I agree. Yeah, right. And especially for these students, right? If they can write out an explanation of something and write out their solution, it's so powerful, that communication. And you have to use precise language, especially when you write it, right? You have to use that precise language when you write, perhaps even more so than speaking. Rudy, I think, yes, I think numeracy is one of the huge, in my opinion, when I teach these, it's one of the huge concepts of these courses. If we can get them to have numerical literacy, even to the concept of understanding that 38 is 3 10s and 8 1s and what that looks like. That's huge for these students. Huge. That's why most of these courses start with a look at numeracy, a look at numbers. Exactly. Okay. Not many people had much to add to that poll, so that's okay. John, can you pull the poll away? And yeah, thanks. Yeah, that number sense to judge accuracy of answers is super important. And just to be able to think mathematically is so important. Okay, so some ways that I try to get out this one with my students is related to what you guys have already said, is to really encourage that precise language and notation. You know, if they're talking about a solution in class, like really ask them questions that delve into, okay, is that really what you mean to say? Is that really how you want to write it? Okay, and this is a great example of a precision question. Which of the following definitions for even numbers is more precise? Definition 1 that is given in some elementary schools, some elementary textbooks, an even number has 0, 2, 4, 6, or 8 in the ones place. Another definition is that an even number is divisible by 2. So in the chat, which one of those is more precise and why? Great point, Heather. Yeah, the first one's just memorization. No understanding is needed, and it doesn't tell you anything about what an even number is, right? And the other number to think about when you think about these definitions is the number 12.3, for example. Oh, Andy, that is a fun one. I hadn't heard that one before. And so if I have the number 12.3, definition 1 is going to say that's an even number, right? Because it's got a 2 in the ones place. Yeah. And definition 2 can be extended to integers as well. And it tells what it means, right? So it's precise. You know, I can't find a counterexample there. But with definition 1, I can find a counterexample, right? 12.3 meets that definition, but it's not an even number. Okay, and then, yeah, what does it mean versus memorizing what it looks like. Yeah, Rudy, but what about the number 12.3? So 12.3 is not an even number, but according to definition 1, it would be. So that's why, the biggest reason why I claim definition 1 is not very, very precise. Yeah, but it's not divisible. But divisible by 2, the way I've always defined divisible, which gets to, okay, with a precise definition, every word should be readily defined, right? But divisible, like if we say that 12 is divisible by 2, don't we mean that it's divisible by 2 because we get a whole number when we divide? Yeah, exactly. It also builds on the definition of divisible, exactly. So that's another thing about precise definitions, right? Are all the words in there, are they have they been defined before? Do they mean what? Well, to put a algebraic definition on even, I mean the algebraic definition is that a even number is in the form 2k, where k is an integer, like that in the chat. An even number is in the form 2k, where k is an integer. So that's a even more precise definition. But of course, that's out of reach for some students. So if it's in the form 2k where k is an integer, then we don't even discuss decimals when we're talking odd and even. And there's debate as to whether -4 is an even number. I've heard a group of mathematicians argue over that fact. So let's move on. I don't want to get too wrapped up in this. We could discuss this forever, right? We're all math lovers. Okay. Are put in the broader category of reasoning and explaining. So MP2 is reason abstractly and quantitatively, and MP3 is called construct viable arguments and critique the reasoning of others. Okay, so let's look more deeply at each of those. So MP2, it says that, again, this isn't word for word, this is interpreted. Make sense of numbers and their context within a problem. And then it talks about being able to decontextualize a problem by representing with numerals and symbols that abstract from the context, and then being able to contextualize the symbolic manipulations by pausing to go back to the context when needed. So, so let's look at this. So in the early years of mathematical thinking, what that means is that you have a context, right? You have 2 cookies, Bill gives you 3 more. How many cookies do you have now? So there's the context. And then elementary students need to be able to basically decontextualize that when they write the equation 2 plus 3 equals 5. So there's no context for that equation, 2 plus 3 equals 5. And that's a hard thing for elementary students and our students, right? When we get into algebra with our students, it's to go from the context, because with the context, most any student could figure it out with that context, small student, that didn't know anything about addition. But then when you decontextualize it, it becomes more abstract. Here's another example of putting it into a context. 261 students going on a field trip. Each bus can carry 36 children. How many buses are needed? So and this is actually a question that was on the NAEP, National Assessment of Educational Progress. It's been a few years. But a huge number of students got it wrong. Because the answer, when you just divide, you get 7.25. And I think it was 70% of students answered 7. Because they probably rounded, right? That's the way they're taught to round. But this is a great example of where they needed to go back to the context. And this is why this practice talks about contextualizing, decontextualizing, going back and forth. It's because you've got to go back to the context to answer this question. Because the answer is not 7.25, it's also not 7. The answer is actually 8. So that's where you have to go back to the context. And you know, how many times have you still told students to write down what a variable stands for, right? X equals whatever, Y equals whatever. So that's a big key in the decontextualizing something. Is you have the context, and then you write the algebraic equation to decontextualize it, but then you always have to put it back into the context. This is a great problem that's classic, right? The old pigs and chickens problems. Okay. But I love this problem because A, there's so many solution paths. You can make a table, you can draw, you can use actual pigs and chicken figurines, you can write an algebraic equation, you can draw models, so many ways. But it's one where if you're going to do it algebraically or even any of the other ways, you have to step back to the context constantly. Step back. Rudy, I'm intrigued by your question. X and Y. Should we use other letters? Is that what you're saying? Not just use X's and Y's all the time? Alright, and then MP3 is construct viable arguments and critique the reasoning of others. So what this one mostly says is that communication strand, right? It's the communication strand of the NCTM. That they're able to use definitions and previous knowledge to communicate their understanding. They can build a logical progression of ideas. If this, then that. And they can use the counterexamples to make an argument. So I've already talked a little bit about counterexamples already. So, didn't bring up the poll a minute ago, but John, can you bring over that poll again? And let's get people's ideas about how to incorporate this one into our classrooms. Let's take a minute. Share your thoughts. Yeah, Brody, I agree with that. Unless you're talking about snakes, because I don't want to use an S as a variable, because my handwriting's too messy. It looks too much like a 5. I like the snake. That was creative, right? So you guys aren't digging this poll, are you? Yeah, I love that. Evaluating work from previous classes, both correct and incorrect. Sometimes I'll have a student, if they did it incorrectly, if they're comfortable enough and if we've built up enough of a safe space, I'll say, come up here and share that and let's figure it out together. Let them figure it out. Error analysis is a great way to promote this one. And error analysis with kids too, right? If you look at student work and some mistakes they've made, especially for these elementary teachers, that can be a great motivator. Great, guys. Okay, John, can you move that out of the way again? Thanks. and I forgot to hit this one before, but a big part of this one is also listening to the reasoning of others, right? But they really, especially these students, they need to listen to other people's mathematical thinking, because that's what they need to do when they become teachers, right? They need to be able to listen to their students' mathematical thinking. So that listening to other people's solutions, because sometimes they're like, oh, I don't want to hear another way because I just understand my way. They need to understand multiple ways, especially if they're going to be teaching. So one question that I often think to myself is with this one is, who is doing most of the talking in the math classroom? Is it the student or is it the teacher? And if the teacher's doing most of the talking, then they're not going to have an opportunity to construct these arguments and critique the reasoning of others. Some I read one time said that right now students do 20% of the talking and teachers do 80%, and ideally we need to flip-flop that. Yeah, clockwise and counterclockwise, that's some time. But with digital clocks, nobody really sees a regular clock anymore, right? All right. Yeah, students use their phones to tell time. Exactly. All right. And provide opportunities where our students are sharing their different solution strategies, and they learn so much from each other by doing that. And a big thing with this, and really all these practices, but probably particularly this one, is that we need to set up a safe space where it's okay to be wrong, right? That's how we learn. And students are terrified of that at first, but it has to be okay to be wrong. And to share that wrong thinking. Like I said, I'll sometimes have a student come up and say, well, I thought this was true, but what do you guys think? And then they'll talk it through and they'll figure it all out. I toured some schools in Singapore, and they do this regularly. When a student gets something wrong, they have the student go up and say, okay, here's what I did wrong, and here's why. Here's why it's wrong, or have the students tell them why it's wrong. This is a great type of question. This relates back to the definition of even numbers we were talking about earlier. Okay? Is the sum of two evens always even, always odd, or either? What about the sum of two odds? What about the sum of an even and an odd? Love doing this one with my students because they come up with so many, first they come up with so many different ways to think about it, which is powerful. And then it brings up, remember the definitions of even? To do this one with the even number has a 0, 2, 4, 6, 8 in the ones place, it's pretty impossible with this one, with that. But if you talk about pairs or divisible by 2, then these become much more manageable. And I've had students that have done this algebraically, pictorially, through reasoning, through blocks. The big thing with this first one is that generalizing is a big thing. Students will say, well, 3 plus 7 is 10, so that proves that an odd plus an odd is an even, but then that can come into a really, really great discussion about, well, just because you prove it's true once doesn't mean it's true all the time. John, I like that. And here's an example that gets really great at that counterexample thing of if a number is divisible by 2 and 6, then it is also divisible by 12. And so students will, maybe try a few examples and say, yeah, it's true. But then you can come into the counterexample and critique that reasoning. Okay, time, so we're going to skip the polls for right now. So, but if you guys have any great ideas for the polls, please, for how to incorporate these, put them in the chats. So the next one is modeling and using tools. We've got these two. So MP4, modeling with mathematics. So this one says that students can solve real-life problems. They can identify important information in a real-life problem and analyze relationships. And they can use models to make predictions, draw conclusions, reflect on, and adjust the effectiveness of their model. So some of the ways that I've tried to get my students to this is just a few examples. Like I say, so many of these are interrelated. But the way I introduce fractions, my first day of fractions, is I give them a whole bunch of manipulatives, might be pattern blocks, circles, squares, base 10 blocks, a ruler, whatever. And I say, model 6/8 and use that model to show me that it's the same thing as 3/4. And so they have to really think about their models. They have to think about what their unit whole is. They have to really delve into the different models and what 6/8 looks like with different models. Similar one is to write 3-word problems for 2/3 plus 3/4. And I do this for all the operations with fractions. They have to write one that is most appropriately modeled as a set model, another one is a linear model, and another one is an area model. And it's interesting, some students will write the problem and then model it. Some students will model it and then write a problem that matches it. It's fascinating to watch that. And there's lots of great misconceptions that come up when they're writing these. It can really be clarified. And then, especially in the statistics, we interpret a graph, right? We use it to make predictions. We're modeling real world. MP5, use appropriate tools strategically. So this one is about using a variety of tools. And tools could be concrete models, technology, paper pencil, a ruler, wide variety of tools to find solutions. Calculators, right? That's a huge tool we use, right? And how to use that calculator, right? So many students don't understand their calculators, don't think about their calculators and how they work. A lot of this is also making a good decision about when and how to use each of these tools. For elementary teachers, it's, okay, when do I want to use pattern blocks? When do I want to use base 10 blocks? Those types of things can come into it. And to use a variety of tools to investigate and develop their understanding. Just understanding fractions with circles does not deepen their understanding. They need to see lots of different models of them. Is there a difference between the word model and MP4, which speaks of real-world problems and using manipulatives or diagrams for naked problems like adding two fractions? You know, and again, these are hard to interpret. MP4 does talk a lot about the real-world problems, but it also talks about using models. And I think maybe MP4 and 5 are perhaps more interrelated than any of the others. Because if you're modeling, you're going to use some kind of tools to model that. It might be graphs or whatever. So I think these are really hard to pull out from each other. I almost just talked about both of them together. Because they're so hard to change. Okay. This is another great problem with this one of this classic handshake problem, right? And I've seen students, they'll get 9 people together and say, okay, you shake hands with everybody. Now you shake hands with everybody. Or they might pull out pictures of people and draw pictures of them shaking hands. It's a great one. You know, and is this a real world problem? Probably not, but it's a great one to model. Right? If you want to model 1/3, do you start with 1 circle or 3 circles? And the answer is you can do either. Right? Or how could you use base 10 blocks to model 34? And how about 3.4? So these are the base 10 blocks. So you could use them. You could use 3 longs and 1 small cube, or 4 small cubes to show 34. But if you change your unit to be the big cube, then how does that change it? So using these models is different. If you can use them for whole numbers, you can use them for decimals, but how you use them changes slightly. Because what you let be your one, your unit, whole, changes. And the final category is seeing structure and generalizing. We have MP7, which is look for and make use of structure, and MP8, which is look for and express regularity and repeated reasoning. And these are probably the hardest in my brain to keep straight as to what the difference is, because they're so much alike. What I've come up with is that MP7 is about finding and using patterns and structures. For example, a kid might notice that 8 times 5 has the same answer as 5 times 8, and then extend this to discover that the commutative property. So it's noticing things like that, noticing these patterns to discover truths about mathematics. And something that's interesting is that young children naturally use structure to make sense of things. Maybe adults do too, but I think especially young children. Have you ever had a student, or heard a young child that said eated or goed as past tense instead of ate and went? Because they've noticed the structure for the English language is usually you put an ed on the end of a verb, and that makes it past tense. So that's kind of a literature, or I guess literacy example of using that structure. And there's a case where the structure led them astray, obviously, right? And sometimes looking at structures in math can lead students to something that's not true. I think a big thing with this MP7 is the mental math activities of being able to look for that structure of math, the properties and such, and being able to solve these types of things. And with mental math, I think it's wonderful to give students these problems and say, figure it out without a calculator, and share your strategies. Let them share their strategies, and they're going to learn so much from listening to their other students. I'll sometimes do this as a calculator game, where one person has a calculator and the other person has to do it mentally, and they race to see who's quicker. And usually someone can do it quicker mentally than with a fraction. And finally, mathematical practice 8. I know I'm talking fast here, guys, but I want to try to finish on time. Is look for and express regularity and repeated reasoning. So this is when, like, we notice that computations are repeated, and we use this to create methods. So to create shortcuts sometimes is what this one is about. And we continue to look at the process and evaluate. And then develop these new methods by generalizing the patterns. So multiplying by 11, for example, it's kind of small, but so it's, what we've done with our students. Right? You look for the pattern and try to figure out how do you generalize that. Right? So 26 times 11 is 286, 35 times 11 is 385, and so you just do the pattern to fill in the rest of the table. Leave that one for you guys to work on too, if you haven't already seen that one. But there you're looking at the pattern and then generalizing it, and being able to use it to do other things. Additionally, what pattern do you see below that will help you add any unit fractions? So again, that's looking for the pattern and then being able to use that to multiply or to add any unit fractions. Okay, so some general comments about the MPs. You guys still please add your comments and thoughts. Is that we need to let our students do much more of the talking than we do. And I know that's hard for us, right? We're really good at talking about math. But we have to sometimes just let them speak, ask them questions instead of telling them. Depth is more important than breadth. You've got to let your students go deep into these. If they're just memorizing and skimming the surface, they're not going to retain it, as Ruth said earlier. Provide access to manipulatives, either tangible or virtual. Have students working in groups. And homework groups is a great way to at least get started with that. Is that when students, when they come into my classroom, they get out their homework and they start working on it immediately. And that just gets them to help each other, to talking about it, to being okay to be wrong with your group. Exactly. Okay. So, to learn more, certainly go to corestandards.org, illustrativeMathematics.org. It's been a great resource for me in this. I'm doing a workshop on these practices where we'll delve more into them in New Orleans next year. Look for that. A lot of the research for this came from my co-authors' 6th edition of Tom Basher and Meg Moss. We worked on this edition, and Chapter 1 is rewritten for the mathematical practices. If you would like a desk copy of that, fill out that more information form, and Cengage will be happy to send you a copy of that so you can read more about this. PowerPoint slides are there. My contact information is at the bottom of the slide, but that's covered up right now. Thanks. But maybe put that form back up, John, so if people want to fill out the form, there we go. And I really appreciate your guys' time. Look at that, I finished right at 4 after talking really, really quickly. I hope you've learned something. I hope you've had some fun. And please contact me. I would love to hear from you guys. And those of you that are like doing research out there in the schools, how these are being implemented, I would love to hear more about what you're learning. Definitely.
All right, well, thank you, Meg, and let's all thank Meg again in the chat room for a great presentation this afternoon. And and Meg, maybe could you mute your microphone?
Yes.
Because I was getting feedback on my end, but thanks to everyone for participating in today's AMATIC webinar, and if you'd like to support future AMATIC webinars, please consider becoming a member of AMATIC at bit.ly/join-AMATIC. And please remember to like us on Facebook at facebook.com/AMATIC. And recordings of past AMATIC webinars can be found at bit.ly/AMATIC-webinars, and it typically takes 1 to 2 weeks to produce and upload webinars to this archive, and all of you will receive a notification by email once that has been done. And if you could please take 2 minutes to evaluate the webinar content and the presenter at bit.ly/AMATIC33. That would be great, and you can click on that link right on your screen, and that will take you to the survey. And if you need email confirmation of your participation in this webinar, please fill in the optional section at the end of the evaluation. So again, that's bit.ly/AMATIC33, and you can click on that link right on your screen. And here again is the link to the information form that Meg was talking about, and a link to her PowerPoint slides. But if anything else is needed, feel free to contact me, and I will pass your information on to Meg as well. That's not a problem. And again, let's thank Meg in the chat room, and if there's any other questions, I'll turn it back over to Meg for a a couple of minutes.
John, yeah, it's just thank you all for being here. Please, let me. I'd love to hear from you guys with any other ideas. Again, I hope this has been helpful. If you have some suggestions, please, I'd love to hear those as well. Yeah, fill out that more information form if you'd like a copy of the text or any other information. And I look forward to seeing you guys in New Orleans next year.
All right, well, thank you, Meg, and I'm going to end the recording right now.